Okay, let's see this question. Which of the following three statements are true? The union of two recursive languages is recursive. So let's see this first statement. This is saying the union of two recursive language is recursive. What is a recursive language? What is a REC language? So REC language is a language which is accepted by halting Turing machine. Halting Turing machines means a Turing machine which will always halt. Okay, whatever string you give, whatever string w belongs to sigma star, whatever string you give, this Turing machine will always halt. It will definitely halt on all the strings. So the language of such Turing machine is called recursive language. Now he is saying the union of two recursive language is recursive. So this is true and we can very easily prove it. Let's assume that L1 and L2 both are recursive languages. So L1 is recursive, L2 is recursive. Because L1 is recursive, so we have halting Turing machine, let's call it H1. And because L2 is recursive, so we have halting Turing machine, let's call it H2. So now what we can do, we can make a halting Turing machine for L1 union L2. For L1 union L2, we can make a halting Turing machine. What we will do? Basically, we will make a new Turing machine. We will make a new Turing machine M. In this Turing machine, what it will do? It will run this H1 and H2, both these Turing machines, H1 and H2. So they will run in parallel. So whatever string you give, for example, you give a string W. Now, on this W, this H1 will also run. On this W, this H2 will also run. They will run in parallel. And now, if at least one of them accept W, then we will say, then this M will also accept. So what we can say? We can say that M will accept if and only if at least one of H1 comma H2 accept. Okay. So this Turing machine M, it will accept W if and only if at least one of H1 comma H2 will accept W. Now you can say that the language of this Turing machine M, this is nothing but L1 union L2. Okay, because either this H1 should accept or this H2 should accept or both should accept. In that case, M will accept. So the language of M is definitely L1 union L2. But now, is this M a halting Turing machine? Is this Turing machine M, is this a halting Turing machine? Yes, it is a halting Turing machine, because what will happen? Whatever string you give, whatever W belongs to sigma star you give, it is guaranteed that H1 will definitely halt, H2 will definitely halt. Okay, and because H1 will definitely halt, H2 will definitely halt, so M will also halt. So we can say that M will halt if and only if H1 comma H2 both of them halt, and in that case M will also halt. Okay, so this is why you can say that M is a halting Turing machine and the language of M is L1 union L2, and hence we can say that this L1 union L2 is a recursive language, because for L1 union L2 we have halting Turing machine. Let's see this second. So this statement is true. Now the second statement, he is saying the language 0 power n is prime is not regular. This is true. 0 power n is prime. Okay, this is a standard non-regular language. This is actually non-CFL. This is a CSL but not CFL, and this is a standard language. But we can prove that this language is not regular using pumping lemma. So very easily we can prove it using pumping lemma. What we will do? Let assume that this is our language L. N is 0 power n is prime. So this is our language L. Now let's assume that L is regular. Assume L is regular. So what we are going to do, we are going to prove that L is non-regular using pumping lemma. So assume that L is regular. If L is regular, then we have pumping length. So let's assume that pumping length is, so this pumping length, this is your K. Let's assume pumping length is K. Now from this language, what we will do, we will take a string 0 power n such that n is greater than this is greater than or equal to K. So basically from this language and this n is prime. This n is prime. So you can say that this 0 power n is prime. Definitely this string, let's call it string w. So this string belongs to language L, and you can say that the length of this string w, that is greater than or equal to pumping length. So this w should be, we should be able to partition this w in three parts, x, y, z, such that all the three conditions will satisfy. The first condition, that is the length of y should be greater than 0. The second condition, the length of xy should be less than or equal to k. And the third condition, x and y power I z, this should belong to L for all I. So these three conditions must satisfy. Basically these three conditions must satisfy, and this such type of partition we should definitely have. Pumping lemma says that we should have this type of partition. Now let's assume that we have this type of partition and these conditions are satisfied. Basically the length of y is greater than 0 and length of xy is greater than equal to k, less than equal to k. Now what we are going to do, so this third condition will also satisfy, hence x, y power I, z, this will also belong to language L for all I. Now what is the length of this x, y power I, z? What is the length of x, y power I, z? The length of this is nothing but your n plus length of you can say length of y multiplied by I minus 1. You can see this is your x, y power I, z. Now the length of x, y power I, z, this is nothing but length of x, y, z, that is nothing but n. Length of x, y, z is n plus I minus 1 times length of y. This is the length of x, y power I, z. Okay. One thing you can now what you can do, you can take I equal to n plus 1, because you know that this condition will satisfy for all I. So we can take I equal to n plus 1. What will happen now? Now it will happen n into length of y multiplied by n plus 1 minus 1, that is n. So from here what you can say n into 1 plus length of y. So this string basically has length this. So you can say this string x, y power I, z, this string has the length n into 1 plus length of y. So now this string belongs to language L, but you can say this string has the length, and the length is not prime, the length is composite. You can say the length is n multiplied by 1 plus length of y. So this is a composite number, and hence we can say that this string does not belong to our language L, and hence we can say that for this I equal to n plus 1, for this I, definitely you can say that this third condition is violated, hence the pumping lemma is violated, and hence we can say that our assumption is wrong. So this L is non-regular. So this is the proof that this language is non-regular, proof using pumping lemma. Very easy proof, there is nothing much. You should know what is pumping lemma, okay, and you can very easily prove it. So this is the formal proof. Anyway, this second language, this is a standard non-regular language. This is not CFL also, because we can also prove it using the pumping lemma for context-free languages. We can prove that this language is non-CFL also. So anyway, that is not required. The pumping lemma for context-free languages, that is not in the GATE syllabus. Pumping lemma for regular languages, that is in the GATE syllabus, and hence that is why I have given the proof using pumping lemma. Okay. So we can say that this statement is also true. Let's see the last statement. Regular languages are closed under infinite union. This statement is false, because what you can do, very easily you can take, for example, in this we have already seen in a previous video, we have already seen that regular languages are not closed under infinite union. In that video I have already mentioned that set of CFL are also not closed under infinite union. Set of recursive languages is also not closed under infinite union. Very easily you can prove it. For example, you can take a language L, and this language L you can take a power n, b power n, n greater than equal to 1. This L, you know, this is a non-regular language. this is a CFL, this is a DCFL language, but this is non-regular, A power n, B power n. Now, this L you can write as an infinite union of regular languages. How can you write this L? Very easily. This L you can write like this. What you will do? AB union A square B square union A cube B cube union and so on. Union A power I B power I union and so on. So you can see that L is equal to infinite union of all these languages. Each language is a regular language because each language is finite language. This is a finite language. Only one string is there. In this language also only one string. So this is finite. This is finite. This is finite. Every language A power A cube B cube. This is also finite. So every language is finite and every finite language is regular. So this is regular. This is regular. This is regular. But their union, their infinite union of regular languages, that is non-regular. So you can say that regular languages are not closed under infinite union. So the answer will be this statement is true, this statement is true, and this statement is false.